Welcome to the video, and we discussed MOSFET's large and small signal models, and then we saw the mismatch in the MOSFETs, and now we could describe the mismatches by two parameters, which is our K, a constant, and the VD. So let's look at how to use these parameters to calculate whatever we want in a circuit, and we will take an example of a current mirror and calculate the amount of mismatch. So we have our current mirror over here where we have our current source, and we want the same current to be reflected from M2, and both M1 and M2 have their omega by L same. So as current mirror is used to replicate exact current, any mismatch error will contribute to the error in the current and will be of some concern. So we have to see how to control the amount of mismatch so that the output is within a certain accuracy. So if original MOSFET has VT1, so let's say due to mismatch, the replica will have some VT1 plus a minute amount of delta V. And similarly, if M1 has a certain current factor K1, so the M2 will have some K1 plus a minute value of K delta K. So the current in the second transistor is given by let's call it not I naught but I2, and which is actually I naught only. So we were hoping that we have a I naught current and we have to mirror it or replicate it as I naught, exactly I naught. But let's say we call it I know I2, and which is basically equal to I naught only, but a little deviated due to the mismatches, and let's discuss that. So I2 can be given by considering the delta K and the delta VT values. So this is a square law model from which I2 can be derived, and we know that the value of VGS is based on K and VT1, and as well as current I naught, and I naught is given by this equation. So now to solve, we can expand this, and but the key intuition to any mismatch calculation is to neglect this. Like when we solve this equation, so we have to neglect the second and higher order terms and keep only first order terms of the mismatch quantities. Example, delta VT square or delta T times delta K are second order terms, so we can neglect that, because after doing this we will get some linear terms of delta VT1 and delta K1, and anyway this delta like these first order terms are very small, so the second order terms are going to be anyway smaller. So instead of solving completely, let's say that we only keep delta K, and for as of now we forget that there is any delta sorry, delta VT value. So let's only keep delta K terms, as anyway we will be neglecting delta K times delta VT terms. So let's say there is only delta K and no delta VT, then the equation I2 will be somewhat like this, and from this equation the effect of delta K is basically I2 equals to K plus delta K divided by K1 times I naught, and this came from this equation and the equation of I naught. So basically I naught is this value, and when we put it in over here we get I2 equals to K plus delta K by K1 into I naught, or basically 1 plus delta K by K1 times I naught, where we can make a sanity check that if there was no deviation and no mismatch, so there was no delta K, and when we make the delta K 0, the total value comes out to be I naught, which is exact I naught, and thus this part gives us the error, and this is basically the nominal value. So now assume that there is only delta VT and no delta K. So what will happen? Our I2 will look like this, and basically it will look like this, where the this part is from like from this part we can say that due to the incremental delta VT, VGS reduces by delta VT, or in other words we can also say that we're incrementing VT by delta VT. This reduces the effect of total VGS minus VT. So as so many terms are dependent on VGS minus VT, so the contribution from this factor is reduced as there is incremental delta VT. So in general, any change in VT can be related to the change in VGS as well without changing the result. So what do I mean by this sentence? So this means that instead of thinking of second transistor as a transistor whose VT has changed to VT plus delta VT, we can say that it has same VT and there is a change in VGS of M2 by the amount of delta VT. And now if there was no delta VT, then I2 would be exactly equals to I naught. But due to delta VT, there appears delta ID. So I through the drain. So like for this gate voltage, we have I naught and we are expecting for the same I naught over here. But due to the change in delta VT over here, we have some incremental current with I naught, which we can denote as I delta ID. And we know delta ID equals to dou I naught divided by dou VGS times delta VGS. And this is our delta VGS. So this is basically our GM value. So this comes out that the small change in the current or small deviation in the current is Gm times delta VGS, where delta VGS in our case is minus delta V. So the effect of delta V is nothing but basically I2 will be I naught minus Gm times delta VT. So if there was no delta VT, then this value will be 0 and I2 is exactly equals to I naught. So now the combined effect of K1 and delta Vt will look like I2 equals to I naught, which is the exact value, minus Gm delta Vt and Y minus. So if delta Vt is a positive entity, then Vt will increase and the quantity of VGS minus VT total will decrease and resulting in lesser current. So minus sign makes sense over here as it will result in lesser current. And due to delta K, this is the effect. And if current increases, the current factor will also increase. And thus, the plus sign makes sense over here. And what is the current factor? So this is the current factor on which the current is directly proportional to. So this is exactly what we get, or this equation is exactly the equation what we get after solving the equation and neglecting the higher terms which we took over here. So now we are actually not interested in calculating the exact value of I2 because each of these have delta VT, delta K, and those are random quantities. So they have Gaussian distributions and around some nominal value. And what we describe is the standard deviation of the distribution. So we have our delta I, we will normalize it with I naught. So delta I by I naught is nothing but I2 minus I naught. So I naught was our original value, and how much how much I2 deviates from I naught is our delta I, which is normalized by I naught. So this is the two factors, and those are also normalized by I naught. So delta I naught in relation to the nominal value of, sorry, delta I in relation to the nominal value of I naught is basically this value. And as Gm, we know Gm equals to 2 I naught divided by VGS minus VT. So thus this value comes out to be minus 2 by VGS minus VT times delta VT times delta K1, delta K by K1. So from here, we can say that Gm by I naught is 2 by VGS minus VT. So now we want to find the standard deviation. So this we like arrived at this conclusion, but what we exactly want is to find the standard deviation of delta I divided by I naught. And when we have uncorrelated random variables from delta VT and delta K, which are not related or correlated anyway, So we assume that the variations are uncorrelated between delta V1 and delta K, and thus we find the mean deviation by squaring it and adding it. So we know that delta K by K1 is nothing but the deviation from our previous derivation, and this value comes out to be 4 sigma Vt square divided by Vgs minus Vt square, and the mismatch in the current mirror is given by sigma square delta I by I naught, which is equals to this entity plus this entity. And from above, from this equation, what we can say is mismatch reduces by increasing the width into length, or basically the size of MOSFET. And there are two factors of mismatch. So one factor is due to a current factor mismatch, which depends only on AK, and Vt mismatch also has Vgs minus Vt square in the denominator, which means if we want to reduce the error or the effect due to the Vt mismatch, we have to operate the MOSFET at larger Vg minus Vt values. So let's take a case where the current factor mismatch is very negligible and AK equals to 0. So let's say hypothetically AK equals to 0 and we have only AVT, and now we want a current mirror with a given value of current, let's say 200 milliamperes. So just take an example. So in order to reduce the mismatch, we would usually say that we will use a larger MOSFET. But for a given current, I naught equals to, this is a square law model, and VGS minus VT square is nothing but 2 I naught by K, where K is nothing but omega cos omega cox multiplied by omega by mu cox by width by multiplied by width by length. So this is the equation we got from here, and when we put this value over here, so our deviation uh, breaks down to this equation, and this tells us that to reduce the effect of mismatch, we have to increase the length of the MOSFET, and there is no other way than increasing the length of the MOSFET. So the physical layout of two matching MOSFETs cannot be arbitrary. We have to lay them out carefully, and so that the parameters are identical to each other. So we will talk about layout of the MOSFETs as well. So now, as we discussed earlier, so the mismatch is directly proportional to, or we can say that it is directly proportional to width, and it is exact. So but the current is inversely proportional to 1 by L, and it is not exact, and it is dependent on some non-linear parameters. But yeah, one thing is sure, that the current, the behavior, is directly proportional to the width. And whenever two MOSFETs are to be matched, so the length should be identical, as we know that the proportionality is not exact and it depends on the nonlinear parameters. Now say that we want this kind of a structure where we have our reference current and we have our MOSFET of 2 micrometer divided by, or not divided by, but width of 2 micrometer and length of 0.18 micron meter. So, and in other side, we have want a replica of twice of I naught, and thus we have 4 micron meter per 0.18 micron meter length. So now one way to implement this current mirror is basically taking one MOSFET and just increasing the width of another MOSFET. So we think that yeah, this will work, but this, in this layout, the current will not be exactly twice the I naught, and due to the edge effects, we will get errors. So the actual way of doing the layout for this is we take three MOSFETs. What we exactly do is we take their width equal and their length also are common, and now what we do is basically we connect two diodes in parallel, and or two transistors in parallel to be precise, and then we add up the current, and this is how we implement this structure and not double the width. So what we can say from this structure is we have omega by L ratio, which is equals to n times. So this is how much in what multiple factor we want to increase our replicant current is n times omega by n divided by L. So this we can say from this that we have n devices in parallel of the ratio omega by n divided by L, where omega by n is usually 0.5 micron meter to 0.8 micron meter. So usually these different devices in array are called gate fingers, and somewhat we can realize them in such manner where we have our um, uh, dopants, and we have our gates like this in n number of array. And if we realize their top view, so we have our channel like this, and we lay our gates or our gate fingers in such manner. And as over here also, if we want to realize this kind of structure, we have three MOSFETs in parallel, and the drain is connected to the gate like this, and the current is input current or the reference current is given from here, and the drains of other two MOSFETs are connected to each other, and the output is taken from there, as well as the gates of all three are connected uh, together, and the drain of first one is connected to the gate, and all the sources are connected to the ground. So here also what we can do is we have drain, source, drain, source, and they all are connected within each others, and all the gates are connected. So this is how we can realize and implement the layout. So basically it will look like this. We have where we have n number of identical omega by n divided by L MOSFETs. So the way the layout is done between two gates, there is a diffusion region. So between the two gates, there is a diffusion region, and which serves as drain of both consecutive MOSFETs. And let's say if that's not the case, so in this case, due to the diffusion layer, over here, there will exist a parasitic capacitance between these two. But as the diffusion region is common in the case we implement, the effect of parasitics is already reduced by half. And let's take an example. So we want to implement this kind of structure again, where we have reference I naught and we want a replica of 2 I naught. So we have we require we have a omega by L ratio, and we want 2 fingers for implementing this MOSFET, and we want 4 fingers for implementing this MOSFET, where we have M1 and M2. So basically, we will have the array of some gates the way we implement it. So what we can say is using first two gates, we can make our M1 and whose gates are connected to each other, and the gate of M1 is connected to the M2, which is made up of 4 MOSFETs, and they are connected like this, and thus this is the drain of M1, and we can say that the drains of M2 can be realized like this, as well as all the sources are connected to the ground. And now we can also say that for perfect matching, we are also using the dummy MOSFETs. So this is how we can realize this structure. And for dummy MOSFETs, they should not carry any current. So ideally, the gates should be connected to the source, as sources are connected to the ground. So that's how the dummies are realized. And in case of linear gradient, which we discussed in the case of resistors and capacitors as well, we need to form a centroid. So we use the middle two fingers for M1 and these two and these two, we use it for implementing or realizing M2. So that's how we also finish the effect due to linear gradient, which would have had caused the error, but now we have reduced it using the method of forming a centroid. And it turns out that there is some asymmetry while dopant is being diffused from top, and the symmetry is between the MOSFET carrying current in this direction. So there are MOSFETs which carry current in this direction, and there are MOSFETs which carry current in this direction while implementing this layout, and there is some kind of asymmetry between them. So to avoid this, we refer using even number of gate fingers. So now let's discuss the speed of the MOSFETs in a very general way. So we hear that the digital circuits become more and more faster with the technology. So let's see if there is a measure of speed in analog circuits as well. So this is how we can realize a small signal model where we have GM. Let's neglect GDS, and we have a capacitance between the junctions of drain and body, and as well as we have some CGS where we put our gate voltage. So assume that CGD is 0. So MOSFET is in saturation region. Now short circuit current, like now the short circuit current gain of the circuit is to be evaluated. So let's say what we do is we apply some IG at the gate and we measure the ID. So when we let's say we applied some current which is in frequency domain, and we have CGS, and it goes to the gate and it induces the current GM times VGS, which is ID. So basically VGS is nothing but IS divided by S times CGS. So this IS divided by S times CGS is nothing but VGS, as S is at source. So VGS is IS divided by SCGS, and ID is nothing but GM VGS. So if we put the value of VGS, ID will be GM by SCGS times IS, and the current gain is ID by IG, which is GM by SCGS. And when we take the magnitude at S equals to J omega, so the current gain comes out to be GM by omega CGS. And now, if we want to see our unity gain frequency, the magnitude is, for example, value of omega where the magnitude is 1, which is also called as transient frequency. So it is given by let's say omega t by 2 pi, which is gm by 2 pi cgs. And let's say at unity gain frequency the magnitude is 1, so gm by omega cgs is 1. So the omega at which we get unity gain frequency is gm by cgs. And now when we have a MOSFET biased at VGS minus VT, so omega t is gm by cgs, and if we put the value of gm and CGS, which is 2 by 3 Cox omega, sorry, width into length. So our omega t comes out to be 3 mu by 2 VGS minus VT divided by L square. So thus the omega t depends only on mobility length and the operating point VGS minus VT. So omega mobility, length, and VGS minus VT. These are the three factors on which omega t is dependent. So as we go to more advanced technologies, the minimum length goes on reducing, and which means that the transient frequency goes on increasing. And if we consider velocity saturation, VSAT, the speed of the carriers, which is basically mobility multiplied by the electric field, and this is called VSAT basically. So in case of VSAT, omega t is nothing but 3 by 2 VSAT divided by L. And in this case also we have to make a decision by doing a trade-off between speed and accuracy and power consumption. So what do I mean by this line is basically we have three conditions. So if you want high speed, omega t is nothing but this equation, or let's say 3 by 2 VZ by L, and this has to be very high for high speed. So for this value to be high, we need a lower value of length, and which means we have to make as short as possible the channel length, and also we need to operate at high VGS minus VT. And thus we say that when we are making the channel length shorter, so we also need small parasitic effects. So this is for high speed, but for accuracy, this is the equation. And for high accuracy, we need to have small variants of errors from these contributions. So long channel length is required and larger width is required, which means we need large parasitic capacitance for accuracy. And for lower power consumption, this is the relation where GM is fixed. So for lower power consumption, we need to minimize ID, and so we need to lower the value of VGS minus VT. So according to our requirements, we need to trade off between these three factors accordingly. So I think that's all for this video. Thank you.